Hi, this is Jared Burdick from Knowles Precision Devices. Today I'm going to talk about device miniaturization on high-K materials. As technology improves, there's an ever-increasing need to make smaller products, from the component level to the system level. In this presentation, we'll go over how designing devices on high-K materials will reduce a single component in size, as well as playing a role in reducing the overall usage of board space by being able to integrate multiple RF building blocks onto a single substrate. We'll also go into the performance benefits of our technology, and we'll provide some real-life examples and capabilities. Here's a brief overview of microstrip technology and how a higher dielectric constant correlates to a shorter wavelength. For design purposes, epsilon R, dk, effective K are all pretty much interchangeable. For design purposes, some suppliers will provide a design value, and that's the value that's going to be entered into your relative permittivity field in your simulation software. As you can see, effective K is really going to drive your size. Here's an example of where we compare the differences in sizes of a 6-order half-wave resonator filter centered at 10 gigahertz filter. Several materials were chosen. The first is a common PCB material, Rogers 4350B. The next is a common ceramic, alumina. And the last three are Knowles proprietary ceramics, each with a different dielectric constant. In this exercise, each filter was modeled to have the same bandwidth, rejections, and the same distance from the edge of the resonator to the edge of the ceramic. This was done to create an apple-to-apple comparison so as to compare just the dielectric constant of the ceramics. As you can see, the use of high-K materials results in a shorter wavelength, and in turn, that reduces the overall size of the component. In order to create ultra-wideband devices, such as couplers or Wilkinson power dividers, typically multiple sections are needed in order to achieve those bandwidth ratios. Take, for example, a requirement of a 10 dB, 2 to 18 gigahertz coupler that needs 7 sections in order to achieve the desired coupling ripple. If you remember from the microstrip theory slide, effective K is really what's going to drive your size in microstrip technology. So here we use an approximate model using effective K as a homogeneous substrate. And that's really going to provide a good estimation to compare the sizes and differences in K, while still be able to maintain the performance that we're looking for. So ideal coupler lines were used, and we compared alumina versus Knowles CF material, which has a K of 25. As you can see, a 35% reduction in size, or at this frequency, that translates to roughly 300 mils length in reduction by simply putting the coupler onto a CF material versus aluminum. Here is the actual version of that 10 dB 2 to 18 coupler and its performance. And this happens to be a surface mount catalog part built by DLI. You can see that the approximate model is very close to the actual size of the coupler. Now I'll transition to the integration portion, where we provide a couple examples of size reduction as it applies to combining multiple RF passives on a single substrate. Basically, you'll see that high K plus integration equals a smaller size, better repeatability, and better performance. So this slide shows some capabilities of what we've done in the past in terms of passive integration. Going from left to right and top to down, we have a bandpass filter plus a low-pass filter. We have high-pass filter plus a low-pass filter. We have a bandpass plus a gain equalization network. We have a bandpass filter plus a Wilkinson. We have a bandpass filter plus a notch. And we have a coupler plus a built-in 50 ohm termination. On the right, we have multiplexers, filter banks, diplexers, triplexers. And then we also have done reduced footprint N-way power dividers. So in the next couple of slides, it'll be shown how integration of a single section Wilkinson power divider centered at 28 gigahertz can vary in performance in 3 different configurations: a single substrate 4-way on Knowles' PG material, which has a K of roughly 12.5, 3 2-ways on that PG material integrated on a PCB, and a 4-way on a PCB where we use Rogers 3003. So similar to our earlier example of the 6-order filter, combining a 2-way power divider on a single high-K ceramic is greatly going to reduce the footprint of the part. Even combining our 2-way filter or 2-way power divider on the PCB will reduce size as compared to building it straight on the board material. And you can imagine the size reduction if you move to an 8-way or 16-way. So how does the performance look like? If you look at the two tables and plots, we used 3D FEM-EM simulation, and there's a lot of benefits in performance when you compare both outright performance and performance over worst-case manufacturing capabilities. So in Table 1, we compare outright performance, and it can be seen that utilizing a 4-way Wilkinson built on a single ceramic will reduce overall loss as well as improved amplitude balance and phase balance. In Table 2, we look at worst-case etching tolerances as to show you what you can expect by performance over multiple builds. So thin film tolerances that were used are plus or minus 0.1 mil, while PCB tolerances we used were plus or minus 2 mil. And for the 3 2-way configuration, we took a look at a plus or minus 1 mil variation for XY location placement. So in addition to the performance benefits, the plots show that not only performance can degrade, but overall bandwidth usage will be limited when using that PCB integration on the Rogers 3003 versus Knowles Precision integration. So in addition to all the simulated examples, here are some real-life components that we built for customers. So on the top, you see there are 2 4-way power dividers at X-band and C-band. And those are built on our CF material, which has a K of roughly 25. Next, you have a bandpass filter integrated with a low pass. And that is built on our PG ceramic, which has a K of roughly 12.5. And then all the way on the right is a 4-band filter bank that has a span going from S-band to C-band, and that is built on our CG material, which has a K of roughly 67. So all of our catalog parts are built on our high K material. They are all very temperature stable, so there's not going to be very much drift over temperature. They're all very low loss. They all have a CTE very similar to PCB materials, so there's no mismatch when you go to mount it on your board. And they are all high quality ceramics, and we also have proven manufacturability on them, so we can drill them. We know the right dimensions that we'll be able to manufacture these with. So that concludes this presentation of device miniaturization on high K materials. Please visit us at knowlescapacitors.com. Thank you very much.